Example 8.3. Question is, find the potential energy of a system of four particles placed at the vertices of a square of side L. Also obtain the potential at the center of the square. Here it is given the system of four particles. All the particles are identical, and we are considering here four masses, each of mass m, at the corner of a square of side L. This is the side L, and for that, just to means we have to find out two things here. First, the potential. Here we have to find out the potential energy of the system, then the potential at the center of the square. So first, to find out potential energy of the system, we will see here there are 6 pairs. This mass is attracted with this and this also. So this mass is also attracted with this and this also. Similar way, you will find here we have 4 mass pair at distance L. That is this distance 1. The potential energy you will find here for this pair, then for this pair, and for this pair, then for this pair. So these are 4. Plus we'll find out diagonally also for this pair also and for this pair also. So for first 4 pairs, we are having the distance between these particles that is equal to L. This is the 4 pairs where we'll find the distance between the particle is L. Now for the next 2 pairs, we have to find out the diagonal, and the diagonal is what? We can find out the diagonal by the Pythagoras theorem, that is L square plus L square, root of L square plus L square, and that is equal to root 2 L. So this distance would be root 2 L. The diagonal of the square is root 2 into side. So root 2 L distance would be there. So the potential energy of the system is the sum of the potential energy of all these 6 pairs, that is U1, U2, U3, U4, U5 plus U6. Here for first 4 pair, you know that the potential energy is given by G mass m into m upon r. So here the masses are equal. M into m is what? M square. For first pair it is, this is G m into m, m square upon L. This is L. Okay. Similarly, it is a potential energy and minus sign would be there. Now we'll see for the next. This is also G m square upon L. This is also G m square upon L. And the fourth one is also G m square upon L. The second one is for this pair, third one is for this pair, and fourth one is for this pair. So, and we know that the potential energy is a scalar quantity. So we can simply add this quantity U1, U2, U3, U4. Now for the next 2, that is for the diagonal, the pair which is in diagonal. So for that U5, you will find that this is Gm square. This would be also minus. This is also minus. Gm square upon. What you will find here? You will find this distance that is equal to root 2 L. So this is root 2 L. Okay. And the sixth one is also Gm square root 2 L. We can add up this 4 easily and this 2 easily. That is minus this 4, the similar quantity is there, that is 4 times of gm square upon L, and this is minus 2 gm square upon root 2 L. So we'll take minus sign common here, and even first of all we'll simplify this second term. This is root 2 and this is 2, so root 2 would be cancelled. Root 2 will remain here, gm square upon L. Now we are in condition to take out these quantities common, minus gm square upon L. Then the remaining one is 4 plus root 2. 4 plus root 2, and this would be the potential energy of this system. Okay, next we'll see the second part of this question. In the second part of this question we will see here, this is B. At the center we have to find out the potential, and potential is for unit mass. That means we'll have to suppose the unit mass here, and all these particles are applying the force on that, and because of that the potential will be there. So at the center of the square, so for that we'll see here that potential is at the center is because of the 4 masses at the vertices, so that is equal to, potential at the center is equal to, you will see that minus gm, will consider unit mass here, and that is why we are calling this as a potential. The distance between this center and the vertices, just half of the diagonal. Half of the diagonal, that means it is equal to root 2 L upon 2. So this is actually equal to root 2 L upon 2, the distance is. Okay, this is for the first particle. Then we have potential for the first, then the second, then the third, and then for fourth particle. So all 4 particles will apply the force on the center, at the center, and so that the potential will be there, and because of that V1 is this much. And similarly we'll find V2 also will be same, because the masses are identical or in all the vertices. So this is also this way we will write. Okay, so we can simplify this also, like these are the 4 times we can write easily. All the quantities are identical, so this is minus 4 gm, and this root 2 will be cancelled, it will give us L upon root 2. This root 2 will go up, then V is equal to minus 4 root 2 gm upon L, and this would be the potential at the center because of this 4 particles system. Exercise 8.12. A rocket is fired from Earth towards the Sun. At what distance from the Earth's center is the gravitational force on the rocket? 0. Mass of the Sun is 2 into 10 to the power 30 kg. Mass of the Earth is 6 into 10 to the power 24 kg. And neglect the effect of other planets, etc. The orbital radius is given 1.5 into 10 to the power 11 meter. So here we will see in the question what are the things given here. First of all, it is given, this is the Sun. So it is given mass of the Sun, that is equal to 2 into 10 to the power 30 kg. Then this is Earth, it is given here. The mass of the Earth, this is 6 into 10 to the power 24 kg. Then the mass of the rocket, it is not given to us, but we'll find out, without this we can find out the answer, whatever the expected from us. So this is the mass of the rocket. I am just considering this m, small m here. Okay. Now the orbital radius. Orbital radius, that means the radius from the center of the sun to the center of the earth, in which the earth is means the radius of the orbit in which the earth is revolving around the sun, or you can say the distance between the center of sun to the center of earth, that is r. It is given r, and the value of r is also given to us. This is given here, that is 1.5 into 10 to the power 11 meter. This we call as a astronomical unit also, that 1 astronomical unit, that is 1.5 into 10 to the power 11 meter. Now we have to find out that the distance from the earth's center, that gravitational force on the rocket is 0. The place or the distance we have to find out. So suppose we will assume here the distance of the rocket from the earth's center is x, where the gravitational force of this gravitational force due to the earth and the sun will be 0 on the rocket. Okay, that means simply 0 on the rocket, that means simply this is the null point we can assume. That means whatever force is applied by the sun on the rocket, that is equal to the force applied by the earth on the rocket. That means they can balance each other, and in that case you will find here, means the rocket here, it will be in the null point. Okay, so we'll find out, that means the gravitation force, we'll write the gravitational force on the rocket due to sun must be equal to due to earth. And what would be the gravitational force due to the sun? That is gm, mass of the sun, mass of the rocket, and distance between them. The distance between them, this much distance is x, so obviously this distance would be r minus x. So it is r minus x square equal to gm, mass of earth, mass of rocket, and the distance between them, that is x square. Here we have to find out x. So you will see that g and m would be cancelled. The remaining quantity will be ms, that is the mass of the sun, r minus x square equal to mass of the earth and x square. To simplify it, we'll just take the square root of both the sides, the quantity. So we'll take, this is ms, the mass of the sun, r minus x will be out of the square root, square and square root would be cancelled. This is me, and here this is also x square, so square and root would be cancelled. Now we'll see here, this is, we'll take the ratio. So while taking the ratio, I'm just taking r minus x here, that is ms upon me, and that is equal to, it is equal to r minus x upon x. Mass of the sun is 2 into 10 to the power 30 kg, and mass of the earth is 6 into 10 to the power 24 kg, root of this 2, and r minus x upon x. We'll simplify it. 2 1s are 2 3s are, this will be cancelled, and 10 30, that means it will come 1 upon root 3 into 1 upon root 3, 2 ones are 2 threes are, so 1 upon root 3, and 10 30 minus 24, root of this also, that is r minus x upon x. 30 minus 24 is 6, and root of this is 10 to the power 3, so 10 to the power 3 root 3, and r minus x upon x, that is 10 to the power 3x equal to root 3r minus root 3x. Will take this root 3x this side, so this is root 3x root 3r. X will take common here, so 10 to the power 3 root 3x, and this is root 3r. Now this time r is what? 1.5. We'll just put the value here, 1.5 10 to the power 11 meter. Then x would be what? That is root 3, 1.5 10 to the power 11 upon this quantity will be just root 3 is 1.73, and 1.73 plus 1000, that will be 1, that will be what? This will come 1. Now if we'll just put the decimal here, that is 00173 into 10 to the power 3 it is. So if we just simplify this quantity, 10 to the power 11 minus 3 will be 10 to the power 8, and this quantity will simplify, it will come 2.5935 into 10 to the power 8, 10 to the power 8, and we'll round off this. When we'll round off this, this is 2.6 into 10 to the power 8 meter. So the distance from the earth center is, the distance of rocket from the earth center is 2.6 into 10 to the power 8 meter. Exercise 8.19. A satellite orbits the earth at a height of 400 km above the surface. How much energy must be expended to rocket the satellite out of the earth gravitational influence? Mass of the satellite is 200 kg and mass of the earth is 6 into 10 to the power 24 kg. Radius of earth is 6.4 into 10 to the power 6 meter, and g is given 6.67 into 10 to the power minus 11 Newton meter square upon kilogram square. So here it is asked to us how much energy must be expended. That means the energy which is required to rocket the satellite out of the earth's gravitational influence. Okay, so for that we will require actually the binding energy between the satellite and the earth. So for that we know the binding energy is what? It is minus of the total energy. That means we will require the energy expended to the rocket must be equal to minus of the total energy, and we know that minus of the total energy, or simply you can say the binding energy, minus of the total energy we have calculated, that is the sum of potential energy and the kinetic energy, and the potential energy and kinetic energy for this rocket or any of the satellite, it came like g m upon 2r plus h. That is, m is the mass of earth, small m is the mass of satellite, and the r is the radius of earth, and h is the height of satellite from earth's surface. All these quantities are given here. We'll just put the value of this, so we'll get the energy required here. That is what it is, minus g is 6.67 into 10 to the power minus 11. Mass of earth is given here, that is 6.4 0 into 10 to the power 24. Then mass of the satellite, that is 200 kilogram. It is given in kilogram. Okay, 200 kilogram. That must be, okay, it is 200 kilogram. So now divided by 2, the radius of Earth, it is 6.4 into 10 to the power 6 meter, then plus 400 kilometer. Here I will change the 400 kilometer into meter, that is 400 into 10 to the power 3 meter, or you can say 4 into 10 to the power 5 meter. So here I will just put the value of h, that is 4 into 10 to the power 5 meter. Now E is equal to, it is minus 6.67. So we can write this as 6.67 into 6.0 into 2, that is the power 10. Here it is 24. This is minus 11. This is two zeros are there, that is plus 2. I am just writing for simplification 2. This is 6.4, 64 into 10 to the power 5 plus 4 into 10 to the power 5, that is E is equal to minus 6.67 into 6.0 into this 2 would be cancelled, that is 10 to the power 24. This is 26. 26 minus 11. So 5 and 15 it is. This would be 15 almost. Okay. And here it is 64 plus 4 is 68 into 10 to the power 5. 10 to the 5 will go up, and this, when we simplify it, it will come approximately 5.9. 5.9. One more thing, that this minus and minus of this would be cancelled. Minus and minus of the total energy. Total energy is coming in minus only. So this will be plus 5.9 into 10 to the power 9 joule. Or if you want to write it in kilojoule, that is 5.9 into 10 to the power 6 kilojoule. So this much energy is required to expand the rocket. Here you will see exercise 8.15. A body weighs 63 Newton on the surface of the earth. What is the gravitational force on it due to the earth at a height equal to half the radius of the earth? So first of all, to find out the way, we will require the effective acceleration due to gravity, that means g dash we will require. What will be the variation in g? So at height, apparent g dash means apparent acceleration due to gravity, that is g dash. This is g dash is given by g r square upon r plus h square. Now given here the height is what? The height up to which we have to take, that is r upon 2, that means half of the radius of the earth. So in place of h we will put the value r upon 2. So g dash will be equal to g r square upon r plus, in place of h will write r upon 2 the whole square. It is g r square and 2 plus 1 3, and squaring 3 3s are 9, r square upon 4. This 4 will go up, g dash, it will go up, it is 4g upon 9. R square would be cancelled. So if actual weight of the body is given by mg. Then the apparent weight mg, which is equal to 63 Newton, it is given here. Then the apparent weight will be, or the effective weight will be, equal to mg dash, that is equal to m multiplied by g dash is 4g upon 9, that means it is mg, 4 upon 9 mg, and that is equal to 4 upon 9 since mg is equal to 63 Newton. So here 9 ones are 9 sevens are and 7 fours are 28. So this is 28 Newton. That means the gravitational force on a body due to the earth at a height equal to half of the radius of earth is 28 Newton.